So hello everybody, good morning. Nice to see you again. So last week we talked about the Islam definition, and we talked about the challenge that we have in Islam. And now you all guys have general perspective of what's happening in Islam and what is the challenge that we are going to deal with. So today we have a chapter, short chapter, that we are going to talk about the coordinate systems. And what's the reason that we are going to talk about it? Because we have the mapping problem of the Islam. That, if you remember, for Islam problem, we want to simultaneously localize and map. And mapping means you need to bring everything inside to the map. And if you want to be able to do that, you need to know about the coordinate systems and what are the different approaches that you can work with points and clouds. Basically, we will have a general and quick introduction of the how different coordinate systems are working and how we can work with them, so that later when we are talking about the mapping, it will be more clear and easier for you. And of course, if we need more details, we will discuss later in the course. So today we are going to talk about first about the affine transformation translation. By default, all of you know these, but we will see how it works. We will talk about the both translation and rotation. Then we will talk about the polar coordinate system and how we can convert Cartesian to polar and vice versa, polar to Cartesian. And what's the reason that we are going to do that? What's the benefits? Also, we will talk about the homogeneous coordinates, and basically in this chapter you're supposed to know how to work with these systems, basically. First of all, we have a question. The question says why we need to know about the coordinates. That I answered at the beginning. Robots have visual sensors, and we collect robot collects visual information from surrounding environment and needs to plot it in the map. And the kind of sensors that we can have also can vary based on what we are going to do. Like we can have cameras, RGBD, LiDAR projector image of the LiDAR sensor that we want to project the 3D image into the map. And of course, points can be in 2D and 3D. We need to be able to work with both of them. And we want to basically know how we can work with a single point on 3D coordinate system. So what is the affine transformation? If you want to have a definition, we can say it's a geometric transformation that preserves lines in parallelism, and also a function that maps affine space into itself. That we want to also keep the dimensionality of each one of the points when we want to apply some movements on each one of the point on the state space, on the space of the map that we have. So basically we can have translation, scaling, reflection, rotation, shear, different elements that we can apply on it, and or any combination of all of those together. So let's start the most basic thing that we can do, transformation translation. That's very clear that if you have 2D coordinate system, x, y, and if you have a point on the coordinate system, if you want to move it on the from initial point x, y to x prime, y prime, what we need to do, we need to apply the tx, ty to each element of the x and y. That is kind of adding some value to them that we can move on the x and y. But how we can show it in matrix form? You can show it x prime, y prime in matrix form. That actually we can multiply the matrix of tx and ty, amount of translation that we want to have on the initial matrix that we have. Like you have x, y, point over there, if you multiply by these, you finally will have this term over here after multiplication. So finally, if you implement this, you will achieve the x prime y prime based on the tx ty that you want to have on the point. So so when your robot is moving on the coordinate system and you want to plot it, you map it, of course, you need translation as one of the basic steps that we have. What about the rotation? If you want to have rotation on the point, of course, in 2D coordinate system, maybe is a little bit harder to understand, but you can imagine if your robot is rotating. But when we are talking about the rotation, you need to also be careful about which dimension and which axis we want to rotate it. So let's say in this coordinate system we have a point. And if you want to rotate this point around the z-axis, what we need to do, okay, let's say we have theta and we want to rotate the this point around theta, around z-axis for amount of theta. What is actually happening? Actually, we are rotating whole coordinate system, and if we draw it again here, you can see that we achieve x prime and y prime, so that after rotation, the point here should be kind of, if like rotating a pixel doesn't mean too much, but if you consider it as object, we rotate whole of it on the z-axis. How we can do that in two-dimensional? Already you most probably studied it. We have single matrix form that we can say x prime y prime can be calculated by multiplying the xy on this matrix here that includes cosine theta, sine theta, negative sine theta, and cosine theta. That with multiplying this amount of theta, you will have the amount of rotation that you will have on x prime and y prime. So this should be very clear and simple for you guys. So for example, if you're going to implement some 2D mapping and you want to rotate your robot on the coordinate system, for each one of the elements of the robot or center of the robot that you have, you can use these simple terms to rotate on two-dimensional. What if we have 3D? If we have 3D mapping, then we need to do a little bit more. First of all, we need to understand that rotation then is not on the z-axis anymore only. Because in 2D, it doesn't matter, like you cannot rotate on the x. Basically, we rotate on the z in 2D. Even if we need to rotate on the x, because it's 2D, just the names of the axis can be replaced. But in 3D, we need to be aware that around each one of the axes we can have rotation. And based on the axis that we are intending to have rotation, we need to use different form of matrices to replace here and multiply by the x, y, z that we have. So here you can see that if we want to rotate the point that we have around x-axis for amount of theta, we need to multiply x, y, z on this matrix. So this matrix have, of course, proof. I'm not going to do it here. You just multiply this and you get new coordinate that represents new point after rotation. For if you want to rotate around y-axis, we do the multiplication by this matrix, and for z1, we need to multiply by the third one over there. Is everything clear? Any question? If you want to study more, I put a link here. By default, you're supposed to know these and how to work with it, but if you have any problem, go check it It shows you how to work with matrices, and more details you can have useful in this link. And of course, nowadays you can find anything on the internet easily. What about the polar coordinate system? Who knows about it? Any of you? Okay, good. So polar coordinate system is a coordinate system that each point on a plane is determined by distance of the point and reference point. So actually, instead of indicating this point over here by x and y, we can say, okay, in polar coordinate system, the distance from the center and the angle from the coordinate system's 0, 0 point center can represent our system, or our point on the map that we have. So how does it look like? So the point on Cartesian was like x, y, but in polar we have r and theta, and that we can show it denoted with different terms here. But r shows the distance between this point, and theta shows the amount of the angle from the x-axis that we have. So now we want to see how we can convert these terms together. That's very, of course, simple. Polar Cartesian system to Cartesian and vice versa. And actually, after calculating the coordinates of point P, we have the r and theta. That let's see how it's happening here visually. So if you have x and y and the point over there, now we want to, in Cartesian system, now we want to convert it to polar. What we do, simply we need to calculate the r, and r can be calculated by Euclidean distance. That simply you say x power 2 added by y power 2, and then we got the square root, and then we have the distance simply. What else? Then we need to calculate the angle. So here I called it alpha. Of course, we can call it theta. So what we need to do, we just simply need to do calculate the arctangent 2 of the x and y. And arctangent 2 usually is very common to use in 3D modeling, and we use it to get the angle of the point that we have in Cartesian system. So you feed the x, y, and you get the alpha over here. That's very simple. So now we can say, okay, r prime, the new after, if you want to do the after conversion, now if you want to calculate the amount of rotation that we have, so the r prime is exactly r itself that we have, and theta prime is the alpha subtracted by theta here. What does it mean? It means that the amount of rotation that we have can be subtracted by the alpha. And if you look at here, the alpha that we calculated over there, and alpha prime, this one, is subtracted by theta. That simply we can rotate the point on the coordinate system of the polar system. Now, what if you want to convert it back from polar to Cartesian? We simply can use these terms over here. So x prime is equal to r prime times cosine of the alpha prime. So and y prime is r prime times sine of the alpha prime. So we take the r prime and alpha prime that we calculated, and then we can take the x prime and y prime based on the after conversion the points that we have in our prime and alpha prime. So now after conversion back, if you want to do apply rotation back again, so amount of rotation that we did here, if you want to revert it or rotate it again, what we do, finally x and y can be shown by this term. X is equal to r prime times cosine of the alpha prime minus theta, that this theta is over here, the amount of rotation that we've done, subtracted by alpha prime. Alpha prime was the first one over here that we calculated, converted, and rotated. Then later we get the cosine and times the distance that we have, new distance that we have here. So this gives us x, and for the y, the same thing, just the difference is that instead of cosine, we got sine. So here we demonstrated how we can convert first from Cartesian to polar, then how to rotate it, then how we can convert it back, then how we can rotate it, to calculate the rotation in order to show the amount of rotation that we have. So before pushing forward, I'd like to show the So next thing that we are going to talk about is the projective geometry that we say calculation is usually challenge, especially if we have not just single point, we have image, for example, to calculate on our presentation. And projective geometry is an alternative algebraic representation of the picture in the coordinate system that we can use it to project it on, for example, other plane, other axis. So actually, when we are using it, we are not changing the geometric relationships. We have the same geometric relationships. We just need to project it on the other planes. And actually, it is dealing with the relationships between geometric images that we have on the frame. So actually, after calculation, we have the same thing on the other plane that requires less computational complexity. If you want to answer the most important reason that is why we are going to also know about projective geometry and use it, is that we can displace a point in infinity on the system. What does it mean? It means that in Cartesian system, can you show infinity point? You cannot show it because you need to definitely have some values on the coordinate system, x and y. But here, you don't need to have it. We will see how we can achieve it. In next slides, I'm going to show the calculations and how we can do that. So we use it for denoting the location of the object on the Euclidean coordinate system that cannot show it, and of course the calculations is more complex in Cartesian system, but here we can calculate it much faster. We will see how to do that. So basically, we want to simplify the whole calculation. For example, here, if you have a look at the this image, so robot sees some view of environment, and this view of environment, when robot is moving, can change. Like I'm in point in this coordinate, I move a little bit, I see again. Everything is same, but it is changing. So that we can instead of working with x, y in 2D, we can work with the Euclidean geometry, so that actually projective geometry, so that we can add one extra dimension to the frame as called as W. That this W is going to help us to project the same frame on different depths on the coordinate system that we have. So what is happening? We have x, y, w, and we add one more parameter to our x, y in projective geometry, so that we can call it as homogeneous coordinates if we have coordinates in projective geometry. So homogeneous coordinates are also famous. You may have heard about it already, but let's have an example how this is happening. In 2D calculations, now we want to add one more parameter. Instead of simply having x, y, we have w. For example, if our image is 810 by 600, we have the parameter 3 here that we added in homogeneous coordinates, so that what is happening actually simply, if we want to project our image, this 3 represents that, okay, just the answer for if we want to project this point over here, the frame that the view, the picture that we have over coordinate system just simply can be divided by the number that we have in homogeneous coordinates w. So we just simply divide it and we have new result. So by adding this w, if we place 1, then we have the same frame. But with adding w, we can project the image in different coordinates that we don't need to calculate it anymore. Because if I tell you, okay, this is the frame, the view that we have in the map, and you want to project it in different depths or different distances from where the robot saw the environment. So simply with adding w, we don't need to recalculate it again in basic, in formal form of the projective geometry. So we say projective geometry in two-dimensional easy to identify because it is 2D and adding 1 is simple. But when we are going to 3D, then you need to a little bit consider more parameters. So let's have a look if we have any point in projective plane that we can represent it by x, y, z. If we have p prime as a geometric object, we can say that it is representative. It is representing the same object in 3D point in 3D homogeneous coordinates on the system where the w, if w is not 0. What does it mean? So let me clarify for you. So we have p prime that is x, y, like a point on the coordinate system. So in Euclidean space actually. So this is Euclidean space. If you have x, y, and 1 over here, that this 1 is the w that we added in the previous slide, we can write it in form of homogeneous coordinate system, that this w, x, w, y, and w. That gives us the x prime, y prime, and w. That this w is representing the here, over here, the value that we have, and we can have it in homogeneous coordinate. So from Euclidean space, we come to homogeneous space with adding one more parameter named w. So if we want to do the convert back, the same thing from Euclidean to homogeneous, we want to convert back from homogeneous to Euclidean. What is happening? Here, as we saw in the example, x prime, y prime, this time we divide it by it. Then we have Cartesian xy in Euclidean space. So actually, one time we multiply, second time we divide it, and come back in the conversion from homogeneous to Cartesian and vice versa. In one single sentence, if I want to explain it, we can say we usually set W1. Basically, we don't need to change the scale of the image on the system that we have. So have a look at the converting back from homogeneous coordinates to Euclidean one. Here is the robot, and here is the Cartesian 2D. So actually, we're drawing a line and projecting it in different W's. You can see that, so that if we have W1, and if we have the size of W1, we can, from the single center point of here, we can project it on the depth that it grows bigger, actually, the calculation. Any question? So what happens if we have it in 3D? Think a little about it now yourself. So it is exactly the same. So here we have 2D, here we have 3D. You just need to apply it on each one of the single points of the cloud. Consider, instead of having the 2D pixel, we have point cloud of the data that we have. Then the same term over here that we have, the calculation, will be applied on all of the 3D point cloud. Then we have the same thing, that if with changing the W, we have scaling up and scaling down simply over there as projective geometry. So therefore, W is the scaling transformation in 3D. So we have a couple of points here that we say it is simpler than Cartesian coordinates. Why? Because in Cartesian coordinates, if you wanna, like, I tell you, if I give you a picture and you wanna draw it in depth x+1, then it's harder to calculate it. But here in coordinate system, we have it by parameter W that is built in homogeneous coordinate. So we have infinity points that can be represented over there. What does it mean, infinity points that we can represent? How we can do that? Do you think? Yeah. We can set W to infinity, exactly, by setting it to 0. If we set it to 0, we can say, okay, this is a point in infinity. Why we need it? Why we need to have a point in infinity? Yeah.
Display all the features that there are.
Uh,
They are out of range for a smaller W.
no. No idea? Hugo?
I was going to say the same thing.
If we define the W at 0, then it will be infinity.
Yeah. It will be infinity, but why? Why we need to totally do that?
Have a more view.
More view, but why? What's the reason?
To make less bad decision. Less bad.
You are close, but answer is not that.
To a better resolution.
Huh? Well, you Googling?
Yes, resolution. To have a better resolution.
No. It doesn't care about the resolution. The reason is, so you have robot, and your robot has LiDAR scanner or some kind of scanner that measures the distance, whatever it is. Sometimes you don't have the distance. It has maximum amount that you can measure, right? And if it's out of the maximum, you don't know if there is or not. And you want to construct a map. And you want to say, okay, that's infinity. I don't know. What is it there? That's the reason that we have homogeneous coordinates, and that's the reason that we have W there, and that's the reason that we have W as 0. Clear? When you have this kind of environment, that it is infinity, and you don't know the measure. So I know here is 5 meters, for example. But when you don't know, then you put, and that's the reason that we have. So we say also a single matrix can represent affine transformation and projective. Also, we will discuss it. All objects can be rotated and transformed by multiplication with one single matrix. We will show how to do that. That's the benefit. And it's a clever way to extend transformation matrix to be square. 3 times 3 matrix in 3D 4 times 4 matrix. That if you go to the details in transformation matrix, we don't have square matrices. That it is challenged to make it square. So with adding one more parameter, we can have square matrices that we can do calculations much easier. So that of course requires one more parameter that we need to add it to also for translation tx and ty that we saw at the beginning. So you can see visually here also that's what's happening. So if you consider the O3 as the center of the coordinate system, so with adding 1 or with removing it, so we can scale on the scale 1 point on the system, the geometric coordinate system that we have, and that's, I think, very clear for you guys. So for infinity far objects, as I explained to you, we can put 0 over there, x prime, y prime, theta prime. As a point on the infinity, we can put it as 0, and that should be clear. And let's now see, okay, I discussed the details and the benefits of the homogeneous coordinates. Let's see the results, what we gain from all those efforts that I tried to explain. We removed the Cartesian. We already know Cartesian XY. That was very simple for everybody. Why we try to learn more to come here, that's the, this is the reason that we have here. So as I explained, we have one single matrix operation that can allow us to do all conversion. How? Let's have a look. We can have, in matrix form, the point that we have, we want to put a matrix here, M, that is 4 times 4, times the homogeneous coordinates that we had, x prime, y prime, z prime, and 1. This was W. So for now, we don't have anything like very complex. X, Y, Z in 3D coordinate system, the point in the space, wherever it is, and 1 is representing that we don't have a scale. W is static. This can be multiplied by the matrix that we want to have it now. And this matrix is going to give us lots of benefits. So what is it? I'm demonstrating the M over here, so that I want to step by step show you all the benefits of homogeneous coordinates. First of all, we want to see how we can have a translation. It means that point, I want to move it on the coordinate system wherever I want, not rotation, not so far. So I can replace this M with this term over here, this simple matrix over here, that you can see first of all, when I was talking about the size of the matrix, that is 4, 4. Now you can see the calculation first of all is simple. So in this representation, I have an identity matrix over here, and the translation vector here. The identity matrix looks like something like this term. The translation vector looks like this one. That if you remember, we have the translation amount on the x, y, and z. So it means that, okay, how much I want to move it on the coordinate system. You just place it here. Here we have 0 transpose, that is the transpose vector of zeros, that is in the form that we define for our homogeneous coordinate system. And here we have delta, that is a scaling factor of whole system that we have. With any value we can have it. Don't mix it up with the w. That that W is the, so you can think about it, what can be the difference, a little bit think about it, then I explain to you. If someone can tell the difference, there can be positive mark for him too, or her too. That was for projection. That projection already is over here, right? But this one is a scale factor that scales whole our procedure that we want to do. Here, translation only, because the matrix that I define here is only for translation. So scaling in the, it's not the depths that I've changed there. It's the scaling of the whole procedure that I have. So they are different, first of all. Second, simply if I want to clarify this part here for you, so we have x, y, z, and 1 in homogeneous coordinate system, right? That we see how to bring it, how to find it. Then simply, if you wanna change the point, to translate the point on the coordinate system, you multiply the same points with this matrix over here. That amount of the translation is written over here. So you just like say, okay, I want to change it 10, 15, 20. Then put the values here, multiply this matrix with the point that you have. Then what you have as a result is, as p prime, is the new point that is translated on coordinate system, but on homogeneous coordinates. Clear for everybody? So the proof why in this form, you need to have a look at the proof of the homogeneous coordinates. So for now, what was it? Yeah, that's hard one. Yeah, since I'm moving, I don't realize it. Okay. Yeah. So again, we had Cartesian system xy, simply points, x, y, z, very simple points. So instead of working for translation and rotation, that first slide I showed you, and I showed you some code. We wanted to make the calculation simpler because if you want to do rotation and the translation plus plus the scaling, it is very hard to calculate in Cartesian coordinate system. To make it simpler, we came and introduced homogeneous coordinates. And in homogeneous coordinates, we saw how we can convert it. How we were converting here. Here. We saw how Euclidean distance can come to the homogeneous coordinate system. So x, y we just multiply by w's, and then we had the x prime, y prime, w by multiplication. So Euclidean space to homogeneous space. Then also we saw how to convert it back, revert it from homogeneous to Euclidean. Now we are seeing what? Now we are seeing, okay, all those things that we discussed, now we are seeing how we can use it. How to use it? We define a new matrix that is multiplied by the point that we have. Then we have the p prime that is translated on the new coordinate system, homogeneous coordinates. Now what if we want to include the rotation? So we keep translation 0 here for now. I put 0 for simplicity. And we want to use and add the rotation matrix. Same form of calculation, the same matrix times the point that we have, the coordinate. Then we want to replace the rotation matrix over here. What is the rotation matrix? At second, third slide, we discussed it. If you want to rotate a point on around the x-axis, we just simply multiply that point on this matrix form here. That gives you rotated on the x. What about the y? What about the z-axis? So this is the object. I want to rotate x, y, and z axis. 3 axes that I want to rotate. You just put the point here, times it, and you will get the rotation. Now we use the same, depending on what we need, which axis we need to rotate, put this matrix over here, or this matrix over there, or that one over there. Clear? So what if we want to do 3 of them all together? So you have a point, you want to rotate it in 3 axes. You just can put merge them together. We can have a matrix that includes all 3 rotations together, so that we can write Rx times, Ry times, Rz times. And of course parameters are different because the amount of rotation that you have different. Like alpha, beta, theta. Amount of rotation for each one of the axes. So actually this here is this one over here. This here is this one, and that one is this one. And as input parameters, you indicate them, and you will have the rotation on the space that we have on the 3D point or homogeneous coordinate system that we have. But the point is, of course, the rotation, the order of rotation is important. So amount of, if you change the order of these rotations, the final point that you achieve will be different. Think a little bit about it. Why?
Answer the question again.
So the question is the rotation of a point on x, y, z. The order is important. You cannot switch them.
then the Z is not at the same place, and the order of rotation will absolutely change for a different spring. So
Mhm.
something like that.
So, correct. Actually, what is happening, because our reference point or the system that we have is static and only the object is rotating, not whole coordinate system. Because of that, if you rotate like x, y, then for example z, so the object will stay like this, right? But if you do the same procedure with same amount with y, x, z, so this time here, here, and here, so I ended up here. So one time like this, one time like this, the same amount of the rotation. So because of that, you cannot change the order over there based what you want. The order should be. So now let's get them together. We just simply put the rotation matrix here with 3 axes and put the translation vector over here that we have 3 parameters for it, x amount of translation on x, y, z, so that we can say we have translation added by rotation that that this gives us on the homogeneous coordinate system and makes everything much simpler. Of course, the calculation for you learning maybe seems more complex, but simply you need to put the rotation matrix and translation vector here. Then we have the final point rotated or translated or both together on the homogeneous coordinate system. So the question is, now we can use this to map the observation. This is not, this is now. So why? Because when your robot is moving in the environment, of course, like the everything getting closer, and based on that, you can plot it. You can map it on based on the need 2D or 3D. Like if you have 3D, you have a scan of the environment, then go scan, then go scan, then go scan. Then you are now able, you know how to do that, how to, if your odometry is accurate, that we discussed, amount of movement of robot, let's say there is 0 error. And if there is 0 error in observation, then you should be able, using this term over here, exactly map the environment. Clear? Everybody? But what's the problem in this course, of course, is that error. That we cannot have 100% accurate odometry and presentation, that we will talk about it, how to fix that issue. One more parameter here we have is the scale factor of object that we can say, okay, now let's see if I can scale the object that is separate from this this parameter that we had here and the W that over there. Think about it, what we are going to do and why we want to add one more factor as the scale. Again, who can say what can be the reason. If you look, you can. So this one that was okay at the beginning, and we added into our coordinate system to convert it from Cartesian. And it was scaling at the beginning because of we wanted to show the infinity point in the system that we have, and that is clear. And this one we said, okay, that's a scaling factor, but for what? For whole conversion problem. Because you have this object here, when it gets closer to me, it gets bigger, right? So translation and rotation together can be scaled. But what if when I'm rotating it, there should be some parameter that I can be adjust with scaling the rotation. Because when you're rotating, the scale can be changed too. Or you should have control to change it too. So because of that, we have the parameter m here that you can apply it on the object in 3D. So may look a little bit confusing, complex, but it is not actually. You just need to use all this term. We have just simply points x, y, z, and this implementation just one time you do. That already also there are many, but you have some assignment. Then you just give the inputs as I did one example. Then you get the output for each one of the points. If you have for one object, you need to calculate for whole object for each independent point on 3D coordinate system. Any question? So finally, in general, we have 7 parameters: 3 rotation, 3 translation, and 1 scale that we can as final point, as final homogeneous coordinate transformation use it. So, do we finished? Only thing that we need here is rotation? Not really. What if we want to do something else? Like if we want to shear the object, like shearing this one. Can we do that? How? Yeah. Okay, but yeah, we can do that. We just need to replace this R over here instead of rotation with whatever we want to have. A valid transformation that we have in matrix form. How? Over here. So before talking about the assignment that you have, over here, for example, like if you want to have no change, you can put this matrix. If you want to translate, if you want to scale it, if you want to rotate it, if you want to shear it in x direction, in y direction, shearing means like, so rotation we discussed in the 3 coordinates. So if you want to shear it in x direction, if you want to shear it in y direction, so you just need to add it over there, add it in the matrix that we have. If you want to reflect it, you can add this form of matrix about x, y, and origin. And this is all the things that you can put it over. But what you have as an assignment, simple assignment that clarifies everything for you, implement the transformation in homogeneous coordinates, translation, rotation, scale, that you need to implement this one simply. And what you need to do, write a class for it, then validate with applying, reversing a point, what I've done on the example, like give the point as input, then then apply, hold the process, then revert it back to see if it's working well and you're getting the same point on the coordinate system or not. And of course, try to visualize it to see what's happening. Not too complex 3D environment, just 2D, or you can do that 3D in Python too, up to you. But I don't expect too much complex things for now for this example. Any question? Is it clear? So for invert operation, you may say, okay, we didn't see how to invert it. Can we invert it that simply? Yes, actually. Actually, one of the benefits that when we are saying the calculations in simple, if you want to invert it in Cartesian system, that's not easy. That's very difficult. You need to calculate everything. But here, simply what we do. So P prime is equal to this matrix times this. We say, okay, we convert it, and we applied very complex rotation, translation, or shear. So now you can do this with simply this matrix. With just implementation in a point, you can do whatever on this space you want, right? We saw it. Simply, you can put reversion and this matrix can be to the power of the minus 1. And if you do that, the same matrix to the power of minus 1 and times it to the points that you have, you can achieve the inversion. Is it clear? Again, you cannot change the order of transformation by the matrix that I mentioned over here too. Same scenario that we had there, we have for reverting operation or undoing operation either. So in this chapter, shortly we saw how homogeneous coordinates are working and how we can convert from Cartesian to polar and Cartesian to homogeneous coordinate system. And with homogeneous coordinate system, we saw that we can add one more parameter w first of all to bring it to the system, and we saw that w can be times in the matrix form, or w can be divided by w. The point can be divided by w to achieve the revert. Then after we bring it to a new system, what we've done, we defined the form of the calculation. That form of calculation gave us the opportunity to do all process of the transformation and rotation together simply. And even we saw how we can revert it back simply, so that anytime when we are going to use work with maps, especially on 3D environment, it's not wise to use Cartesian. Mostly we go to the homogeneous coordinate system and work with it. Okay, any question in this chapter?